The topic I wanted to talk about today is sort of building towards higher assurance silicon. The original topic was end-user verifiable silicon, but I've actually been looking for a term that sort of encompassed the overall sort of goal of what I've been trying to do for the past few years in my research. And I came across this term, hanging out with some cryptographers. They're using this term, throwing it around. It's kind of a big tent term. And it's kind of a philosophy of kind of structural correctness. So it's kind of the analogy is like, programming in C versus Rust. So Rust is a memory safe language. You eliminate a whole class of bugs. And so that would be like a higher assurance language. You're not doing a bug hunt to try to find things, but like you're eliminating classes of bugs by using the right methods and the right languages for it. Or like in cryptography, it'd be like doing formal verification. So actual proofs that your cryptography is correct versus like fuzzing and searching for what's going on. So a number of the principles that I would say are sort of embodied by high assurance are things like structural correctness, verification based on evidence. So open source is an important part of that. Sort of fault resistance. Auditability is part of it, but it's not like it's just about auditing. It's about having the evidence and the proof to be there. And also just making things audible, so sort of like minimal and clearly specified, right? So anti-principles of high assurance would be things like trust proxies, things like brands and labels. Like, you can trust this because it says blah, blah, blah company on the outside. Or this label here says what it is, therefore you should trust it. Things like NDAs are anti-principles. Things like certifications. Certifications alone are not basically what you build high assurance on top of it. It needs to be some meat behind it. So a real world example of sort of a high assurance project is a project called Fiat Crypto. Have any of you heard of this, by the way, Fiat Crypto? It has nothing to do with Bitcoin. Okay, it has nothing to do with like it's actually, they picked the name before Bitcoin came out, so it's like the worst namespace collision ever. But basically it's a compiler for elliptic curve cryptography, right? The compiler is proven in rock. So it's actually formally proven compiler, no bugs. Either way, basically when you put a bunch of parameters on the inside, it either outputs valid code or an error. Those are the only two outputs of this thing, right? And so part of the reason why, remember back in the RSA generation, we had like this long series of implementation errors and all this sort of stuff. When we got to the elliptic curve generation, a bunch of researchers got together and says, like, we can do better than this. We can actually prove their compilers are correct, and we can actually generate provably correct mathematical code. And this is one of the outputs of it. And outputs into several backends like C and Rust, whatever. It's what they use inside boring SSL. It's the stuff that you're using right now inside of your browser in Chrome or whatever it is. And this is part of the reason why we don't have a whole series of papers about breaks upon this particular crypto system, is because these people use high assurance principles to go ahead and make sure it's correct by construction, correct up front, right? So this is an example I find of like, I found really compelling and sort of like embodies some of the principles I'd like to sort of bring more closer towards what we're doing in hardware, things we're trying to strive for in terms of correctness. In contrast, silicon, while designers of silicon might do high assurance techniques internally, to the first order on the outside, customers have no assurance, right? So if someone presents you a secure enclave chip or whatever it is, what evidence do you have to believe that the chip has what you think it says on the outside, right? We basically have to take the designer's words at face value, or best for trusting a third-party certification to go ahead and tell us what's going on. And there's to a first order of no ability to sort of verify any aspect of silicon, the firmware, the supply chain, and so forth. So personally, I've encountered some of these conundrums in the past. In addition to doing sort of research and security and design work, I've done some manufacturing. And so this here, for example, is a chip which is ostensibly supposed to be some sort of cryptographic chip or whatever it is from ST. Someone was saying, geez, this chip, I put it in, it just gets warm. What's going on the inside? So we go ahead and decap the chip, and inside the label on the inside is an LCX244 or something like this. Which is like an 8-bit octal buffer, right? So, when you have a chip and you just bind them based upon the labels and trading on these types of things, you don't really know what's going on. There's no real assurance that the product you have at the end of the day. And fundamentally, as people are starting to see more and more today with the geopolitics and the supply chain stuff, 10 years ago, no one knew what a supply chain was. No one knew where factories were, what fabs were. I had to explain to people what a fab was. I had to tell people what DUV was and these sorts of terms. Now it's headline political stuff, particularly here with the cradle of ASML, whatnot going on. But as we now know, supply chains are complicated, they're global, and they're vulnerable. Chips, start their design process somewhere out, in the middle. Pick your country where you want to be, like United States, China, Taiwan, and then they go through fabs. They're located in other parts of the world. But that's not the end of the story. After they go through the fab, they have to go through packaging. So they might get sent to Vietnam. They might get sent to Malaysia. They might get sent to Singapore. The actual design house themselves are in none of those. They might be here in Europe. They might be here. They might be out in Asia. They might be in the United States. Those things then go through a very complicated web of gray markets, traders and whatnot. And the gray markets are absolutely essential for the companies to function. Those guys can't predict their volumes perfectly. And so they serve as a buffer for inventory going back and forth between people. It's kind of what allows them to meet their financial reports at the end of the day. So as much as you want to say, let's just get rid of the gray markets, they're just simply not going away. This is why, it fell off the back of a truck. Why did I get this? How to get this piece of hardware is actually a really viable answer for a lot of people who are doing hacking. And then finally they end up, in a factory being fabricated. But even from there, it has to go through a customs officer. So there's a geopolitical checkpoint, potentially an adverse one, who will 100% have access to your hardware, goes through a distributor, and then you have customers in your area, right? So when people buy stuff and they go ahead and say they don't want it or they want to return it, they can actually modify it, tamper it, and then put it right back into the supply chain. So you don't even have to be all the way on the production side. You can be on the consumption side. A tourist with a suitcase full of hard drives that have, some programmed SSD firmware on it. You can just buy them off your local distributor, swap them out of the case, put the tamper label back on, and then return them back to the vendor. And guess what? In a particular area where a bunch of data centers happen to be, there's now a bunch of hard drives that have firmware on it, and that didn't require any sort of state-level adversary. You just needed someone with a suitcase and a bunch of hard drives in the right area buying stuff off your local distributor. So when you're given a chip and you say, okay, what is on the inside of this chip? What assurance do you have, right? How do you know what is going on inside that chip? So the question I have is, can we do better than that, right? Like, is this really where it ends? At the end of the day, I'm not here to tell you that's where it ends, obviously. I think we can do better than that. So one of the prongs of the high assurance work that I'm interested in is sort of basically doing a high assurance supply chain, basically going away from labels and coming into direct inspection of silicon, right? So there's a technique that I've been investigating. I call it IRIS, infrared, in-situ verification of silicon. It's a method for inspecting certain types of chips after they've been attached to a circuit board and without damage. So you use the chip that you're inspecting. This is different from taking a chip and decapping it and layering it down because you have to throw that away after you use it. This one is actually a chip in a product as you received it. So this little loop here that I'm playing shows, you'll see a picture of a circuit board in natural light. That pinkish color is an infrared illuminator turning on. And what you can see is as that illuminator turns on, you can sort of see those little ghostly like reflections off the chip. You're actually seeing through the silicon and seeing like the metal layer that forms the transistors in that image. And then at the very end of the loop, you can kind of see, I took a picture and blew it up. You can see there's texture. You can see there's elements in it. This is a touchscreen controller for mobile phone. You can see the different channels of the ADCs and DACs very clearly in this image. You're going away from just saying, oh, this is some Broadcom chip to actually this is the structure of the chip on the inside. So that, to me, feels much more like a high assurance that the chip is what it is. It's not 100% insurance, but it's way better than just looking at a label. So then what kind of chips can we inspect with this? The short answer is the shiny ones, right? So if you're not an expert in packaging types and whatever it is, chips that look shiny and basically have exposed silicon on the backside are inspectable with this technique. The technical terms for the packages are wafer level chip scale packages or flip chip BGAs, these types of things. They have exposed silicon back, ideally with no paint or film on the backside because the infrared light has to get through, and ideally polished and thinned, and they would need to use a lightly doped substrate. That's the other kind of subtlety. The good news is basically that's all of TSMC's chips, which is like a lot of the chips out there. The significant exception to the rule is like Intel has a very heavily doped substrate, and so those chips need to be very much thin before that light can get through them because there's too much scattering from the dopant in the substrate. This does not work on plastic packaged chips. So it's not a technique that will just go ahead and retroactively check every single chip in your system. I've had people come to me and say, hey, can you check this chip? And it's like, some QFN in a plastic blob. It doesn't help those particular things. So it's a technique that we can use to apply to get higher insurance, but we have to be aware of it. We have to want to use it. We have to ask for it. So part of the thing, by talking about it at a conference like this, I'm hoping people become aware of it who have a threat model of supply chain and say, actually, can you as a manufacturer please provide this in a package conducive towards inspection? The good news, chip scale packages are a very high performance package, very low cost package and volume. So it's not an unreasonable thing to ask for. So how is this possible? Is this a magic trick? Obviously it's not magic, it's physics. Silicon is transparent to infrared light, so that the visible image on the left there, you can see, taking normal light, when you turn on the infrared emitter, you can start to see the patterns of the silicon behind it. This is a graph of the absorbance of sort of silicon with respect to wavelength of light. So on the left-hand side of that graph is visible wavelength. So the absorbance is very shallow. The amount it can get through is very shallow. So maybe 10 microns. A micron or so is as deep as the light gets. But as soon as you get to this window starting around 1,000 nanometers, you can get through a tenth of a 0.1 millimeters to a millimeter up to a centimeter, that kind of thing in that range. And then beyond that, it gets way, way transparent, like super, super duper transparent. And so the nice thing about the shorter wavelength range is that actually there's a bunch of standard CMOS sensors that are actually sensitive to light in this range. So this here, if you have seen those surveillance cameras that kind of dot around a lot of these buildings and whatnot, a lot of them work at night. They're kind of night vision cameras. They don't literally see the heat of our body, but they have infrared illuminators that can illuminate in about 1,000 nanometer wavelength. And the idea is that actually regular CMOS will just detect it. It's just a property that it has. Most cameras, like the ones on our phone, actually will work in infrared, but they have a filter that cuts it out. Because the problem is if they don't have that filter there, depending upon the amount of infrared light, you'll start to get like a reddish hue in the images, which is considered objectionable by most humans. These surveillance cameras actually, instead of attenuating the light off to the right-hand side, so you can see on that graph there, you can see that there's a blue, there's a green, there's a red band, right? Instead of rolling off at that sort of vertical bar that I showed there, they actually go all the way up to fully transparent. To gather as much light as they can in the infrared, and they start to roll off. That roll off on the right hand side is a natural sort of attenuation of silicon with interacting with photons with wavelength. And so you can see at around 1,000 nanometers, they're about 30% efficient, but they've actually got all three color elements working at the same time, so they have roughly the same efficiency in terms of collecting light. So this is a cheap sensor. So we're not talking about you've got to buy a gallium arsenide, super cooled, cryogenic, $10,000 kit. These are like the little microscope cameras you buy off of wherever, like online website for like $50. You can take the filter off of it and it'll do this trick. This is not an exotic piece of technology. So putting it all together, the overall scheme of Iris, very, very simple, right? You just, you take a 1050 nanometer LED, you shine it on the backside of the silicon, and it sort of, so this is what I show you is a cross-section of the silicon. The very bottom side is circuit board, some solder bumps, and there's the chip, and the chip is face down. The light comes into the backside, interacts with some metal on the backside, reflects off, and goes into the camera, right? The key thing is that you can now inspect chips after they've assembled to your circuit board. You don't have to take them off your circuit board. You don't have to destroy the product. You can basically just check it after it's in your product and then use your product. So you're not doing sample checking, you're doing direct checking of the chip you're going to use. So in terms of looking at the chip from the backside, I would say this is actually the correct side you want to look at the chip from. If you look at a chip from the front side, as you can see in the top middle diagram up there, you have the solder balls, they're blocking large portions of the chip, and then you have a whole bunch of power distribution networks. Basically, you see is a bunch of metal mesh that sort of relates roughly to stuff underneath, but you don't see any structure of what's going on at the end of the day. When you look at a chip from the backside, you actually can see individual transistors. So the image on the bottom is an infrared image of a chip from the backside, and I kind of zoom into a spot there. You can see that little tile of like 9 squares. That's part of a band gap. Those are actual individual transistors, part of an analog circuit that you're looking at with the infrared. And so when you can see the actual transistors, it gives less room for an adversary to go ahead and hide something on the inside because they don't have the transistors to hide stuff in. They have to use the transistors that are there for any attacks they want to craft. So that's what it gets you at the end of the day. So how would you implement this? How would you go about doing Iris? Here's a couple implementations I've put out there just as references. If you want to do like a fully manual setup, so basically you just get a camera, stick it on like a little sort of stand or whatever it is, and a monitor, less than 300 euros for this thing. So there's a little, it's called an MZO, monocular zoom microscope. The cheaper ones, the better. Actually, the fancy ones have anti-reflective coating that are optimized for visible light. The really, really cheap ones have no coatings, and so they work great in infrared. So get the cheapest one you can find. They work good enough. A random sort of inspection camera scope that I got off the internet. You just pull off the infrared filter. It's a little sticker you can pull off, stick it on there, and you're ready to go, right? So depending upon the price and how much you want to go into the stand or whatnot, probably half the cost of this is the stand, right? And then if you want to do something a little fancier, I put out an open source design for a thing that can do fully automatic adjustments, and do very repeatable measurements. But the manual adjustments part is quite good enough. So here's a little GIF loop that I have of one where actually this is a standard Sony Alpha 5000 camera body. Again, that has an infrared cut filter on it, which I removed. And then when you remove that, it's now visible I can see through the infrared. And what I'm doing inside the image is I'm taking a light, which I stuck into a little white LED thing, just retrofitted the infrared LED into where the white LED was. And I'm sweeping it across a chip, and you can kind of see how the light is playing across a chip. It's an Apple chip, which is like a PMIC from a motherboard. You can see at the very top, there's like a set of like white rectangles. Those are the driver transistors for like the buck regulators that are used inside of the chip, right? So you can actually just on that device see them already. You can generate pretty high quality images, but it's it takes a little practice. It's a little, the repeatability is not great. But if you're just an end user and you want to get some assurance that this product is the product you think it's going to be, I think it's absolutely suitable for that sort of thing. And it's great for the case where if you say, what's the story for getting to every single person in this room and they want to check something, this is the story you would tell them. It's like you just buy this thing, modify it, or have a friend do it, have a hackerspace have one of these, and you can do the checking of it. If you want to get fancier, I have this open source rig that you can get where the light sources themselves are CNC controlled, and the device can spin around and find the different parts of the chip automatically. Has better than 10 micron precision repeatability. It's good for generating the reference images of a chip. So if you want to sort of tell people what is a chip that you're looking for, what it should look like, you can use this type of thing. If you have a high throughput screening situation, or if you're running a server farm, you want to check hundreds of chips or something like this, is the kind of thing you might want to get a jig in one of these things. So one really interesting thing is people will observe photons are large. 1,000 nanometers is very big compared to a transistor, right? It turns out that what happens when the photons interact with the standard cells is that you're basically getting a hologram. You're getting a sort of a sub-wavelength diffraction pattern that relates to how the light plays with the chip. And so this image loop here is what I'm doing is I'm taking the light source and I'm rotating it like this about the axis of the chip, right? And so you can see versus the sort of the incident position of the light, the actual reflectance of the different standard cells would change depending upon the orientation of the metal within each particular standard cell. So in addition to just getting a static single image of the chip, it really depends upon what angle you're illuminating the light from, and you can get more information about it than you can just considering it as the absolute magnitude of the light. Basically turning around, getting the phase information, incorporating it into the analysis can give you more idea about the structure of a chip than just looking at the static infrared image alone. So you can do something at the sub-wavelength level. And here you can kind of start to see some of the structure of the standard cells and the fill cells on the chip. If you want to look at some sample images, I uploaded to a server called siliconprawn.org. You can go ahead and check them out and sort of see what you might be able to do with a technique like this. But you get sort of an idea of what's going on here. In terms of what the standard cells look like, this is a Sky 130 process, 130 nanometer, pretty old, but the standard cells here are huge, right? You can really see every individual cell. So I've taken a image on the left, I've overlaid upon it sort of data I've extracted from the GDS on the right-hand side here, and labeled a couple of different cells. You can clearly, kind of call out different fill cells, flip-flops, logic gates, these types of things. So we can see some standard cells. We can't see how they're wired together. Right, so we're only seeing the transistors that form the logic underneath, but you can actually see the cells themselves, which is a big, not perfect, but it's big progress from just being it says trust the chip on the outside, I'm going to trust it, right? So it's a big step forward from that. Now, as open silicon matures, I think we can do even better. Beyond if your primary threat model is supply chain, right, you can employ things like electrical scan chains. Of course, if you're worried about keeping secrets, scan chains are a different compromise path, but you can choose to have some parts of your chip scan chainable or not. Are people here familiar with the term scan chain of JTAG scan? Okay, so basically when you have a circuit, you have a bunch of flip-flops on the inside. You can rewire them so instead of them working in the normal logic mode, they actually form a big shift register. They just sort of shift the bits through. And then you can sort of say, okay, I'm going to put a test pattern in. I'm going to let the logic do what it does, and then sample the test pattern with the same scan chain and read it out. You compare those two patterns together, and it tells you what the logic is doing in between each one of these chips. So it's an electrical way of determining if your chip is correct or not. Every chip goes through this on manufacturing to look for manufacturing defects. Now, you may ask, well, if we can do this, why do we even need infrared inspection? Why don't we just do this all the time? The problem is when the adversary also knows when you're checking, right? So if someone put a Trojan into your chip, they have access to the signal that says, I'm scanning, right? And so then you can basically build a scan chain which says, when someone's scanning, go ahead and be honest. When someone's not scanning, go ahead and be dishonest, right? So what the infrared inspection does, it says, I can prove there is not the existence of the logic that would be sufficient to go ahead and fool my scan chain check. Right, and so you then make your scan chain checks arbitrarily complicated to the point where the logic to bypass it has to be quite large, and then you can go ahead and say, okay, between a scan chain check and an infrared check, I have full confidence that this chip is actually correctly constructed down to the electrical level at the end of the day. So that's kind of cool that we could do this with open silicon, but then when open silicon, right? You know, silicon's still a very famously closed industry. So I'm going to share a couple of reflections on this before getting into the last part of my talk. So Moore's Law had a clear inflection point. I mean, some people argue with me still. They think that Moore's Law is alive. Like, I think it's clearly dead and under the ground for quite a while now, and the corpse is rotting. The transistors basic, for me, my defining point is where the transistors stop getting cheaper, right? Around 28 nanometers. Is when basically you had the same piece of silicon and you put more transistors in and it cost the same, right? Beyond that, we put more transistors in. True, we did put more transistors in, but we started paying more for those transistors at the end of the day. So this is pretty well illustrated by a couple of die shots here. Pre-28 nanometer, you spend $300, you got 9.5 million transistors in a Katmai CPU. 1 year later, you spend $300, you get 28 million transistors in the next node. Like, 3 times as many transistors, great, for the same price. Post 20 nanometer, this is around 2020, you buy a GPU, 17.4 billion transistors is what you get for $300. To get the same level of transistors, that improvement in the next generation, you paid $900 for it, right? So you do get more transistors, but you are paying more for those transistors, right? So there's a certain clear point. There's a one node, magic node, where things basically kept the same price. And so this is around what I call the 28 nanometer node. I say in quotes because the 28, 22 in that range is what it is. And this is the range where transistors were the last, what they call planar FET nodes. These are the last conventionally scalar CMOS transistors are printed. And the key cool thing about them is you can print them with a single DUV mask layer, right? You don't have to do double patterning. You don't have to do quad patterning. You don't need EUV, whatever it is. It's the simplest transistor you can make. Using the kind of classical techniques. It's the end of classic Moore's Law scaling at the end of the day. And so there's this node basically for the foreseeable future will continue structurally to be the cheapest node. Any node later than that had to use more expensive steppers, more mask steps, whatever it is, you're going to have a higher cost per transistor. So forever from now on forward, this is going to be a special place in the semiconductor industry. And it's reflected by the investments that fabs are putting. Like, they're putting a whole bunch of investment, building lots and lots of 28 nanometer capacity, because eventually they all want to deprecate the older nodes and say, if you want to build a cheap chip, this is the node you're going to use, right? So the good news is that a forever value node is a great news for people who are doing open source. Open source takes time, right? These are volunteer projects. People are unpaid. They're not on VC funded like timelines trying to go up and right. So it can take 10 years for a project to reach maturity. 10 years is forever in silicon. Right, if you start something like in 2000 and you tape out in 2010, right, and you stayed in the same node, no one's going to care, right? This is part of the reason why we didn't have open source silicon, is because you just didn't, by the time you'd made up a tool, no one cared about it, right? But now, in this value node, if you take 10 years later, you're still enjoying the same cost benefit that everyone else is doing in the closed source domain. But if you look at the cost of a tape out, a significant portion of the cost of the tape out is the cost of the tools, is the cost of the software, is the cost of the IP. So this little graph I show here is like the relative cost of tools over time, and sort of those some of those colored numbers show like the relative cost of tools. I put X's over the regions of the things you're not paying for in open source silicon. So the cost of your tape out goes down by over 50% using the open source tools when they become mature. And that means that when you come out with that product at the end of the day, you will have a structural advantage over the closed source companions. And so this is actually a compelling business case now for open source in silicon, which didn't exist before the last node of Moore's Law. And there's this question about IP, right? And the fun fact is that Mickey Mouse didn't make chips. Hooray. So people are kind of aware of the fact that copyright is like author's life plus some obnoxious number of years, which basically means we're never going to be able to own anything that we read in our childhood, right, at the end of the day. Turns out Mickey Mouse didn't care about chips. The chips still have the original term of copyright that was intended for things to have 10 years, right? So those chips that were taped out in 2015, today you can reverse engineer them, and they are public domain. They are open source at this point in time, right? You can go ahead and do that to those chips. Patents have a 20-year lifespan. So the fabs that were built 15 years ago, all the IP that was going into all that patented stuff basically becomes public domain in a few years, right? So pretty soon, even if we don't have the PDKs, even if we don't have the source code available, we will be able to extract it through reverse engineering means, and we are legally able to use those items to build chips at the end of the day. So this is also a very interesting inflection point. This is why the timing now is so interesting for doing open source in silicon, is because this value node is going to be around longer than the mask rights, longer than the copyrights, longer than the patent life, right? And so this image here, I have here on the left is like a little micrograph of a SRAM cell from a 28 nanometer node that was taken over 10 years ago. So if you want to go ahead and extract the mask pattern from that and publish it, fine. It's a mask pattern, 10 years copyright. You're done. You're free. You're allowed to do it. It's public domain, which is not something I can say about most other copyrighted things in the world. Still, we're a few years off from a fully open PDK in a modern node. The state of the art is 130 nanometers, as I had indicated earlier with some of the diagrams I had shown. You can actually today, if you're interested in getting into silicon, there's a program called Tiny Tape Out that exists. They have you can just start playing with the rules and design kits, get familiar with all the terminology, the lingo, whatnot. It's a relatively low fee to participate in this type of thing. It's a multi-project wafer. And because they're using scalable CMOS rules, the things you learn in 130 nanometers scale very well down to these smaller PDKs. So if you have any interest, think you want to go into it, you have a little extra time on the weekend, I encourage you to go ahead, check out these projects, start playing with it, because as these PDKs start to come online, you can have your skills refined and sharpened and ready to go to match up when that momentum comes to reality. Now, in terms of getting open RTL chips done today, which is my interest, I want to get some open RTL out there. There's a concept that I've been playing around with, which is called hitchhiking on a tape out. I call it hitchhiking on a tape out. So tape outs are famously expensive. So a mass set at 22 nanometers around $2 million, something like this. I don't have $2 million to tape out a chip as a hobby project. No way, right? But the cost of a silicon is not by the transistor, it's by the area. It's like doing a photocopy. If I do a photocopy of a page and I only put a haiku on it, I pay the same price for that page versus if I put a whole page of text on it, right? So if you can cram more text on the page, you pay the same price at the end of the day. And the thing is, the area of a chip is oftentimes determined more by the pad ring, the number of I/O you have, or the hard macros, the amount of RAM you have, than the amount of logic, right? And then also you consider the fact that like open RTL is free as in beer. So if I want to go ahead and put some open source RTL onto a chip, there's no licensing, there's no royalty issues to deal with it, right? So if you have a small hole in the 22 nanometer chip, maybe you could stick something in there. So I've shown here a diagram of like a typical very high level SoC, like, you have the Cortex M7 sitting up top, some CPU, you have some bus fabric called AXI, which go ahead and connects everything together, and then you have some peripherals and some RAM and some ROM. That's what like a chip might look like. The question is like, could we introduce into here like another CPU on top that has an open source heritage on it, right? Can we just plug it into this multi-master bus standard, and then what's the cost to what's going to be the cost to introduce this optionality at the architecture level, right? Turns out it's very cheap, right? So like a VEX CPU on a 22 nanometer process and the tape out that I was working with is about 2% of the gate count and no extra die area. There's no extra fabrication cost. And what you get for putting this on here is you expanded market reach. You now have a polyglot SoC. It speaks ARM and RISC, so depending upon what your software base is doing. And if you do throw in, like, for example, a RISC-V that has an MMU, all of a sudden you have a chip that couldn't run Linux, and now you have a chip that can run Linux, right? So you actually have, like, a much bigger market reach as well. So there's some compelling reasons for commercial companies to consider talking to little guy like me and say, hey, let me put an open source core on top of your SoC. You have more market reach with the same tape out. So in practice, I actually did manage to have this opportunity. This is a image of, kind of like a high-level image of what the chip is. These larger blocks, you see the big rectangles, you can really see those are the memory blocks. So you can see this thing is really limited by the amount of memory on the chip, not the amount of logic. So I introduced onto this chip one open source Vex Core CPU and 4 Pico RV32s. Those kind of orange circles call out where the logic is. And I also sort of put a very, very, very zoomed in image on the left-hand side here of sort of what the logic density looks like. You can actually see that the actual density of logic is quite low. You can see that gray is like empty silicon, dark silicon, and the color blocks is where the actual silicon is. So when we introduced these extra logic blocks, basically things got a little bit more dense, a little more. The routing was a little harder, but it wasn't a big problem to go ahead and put these in here. So at the end of the day, I was able to sort of hitchhike on top of this tape out. So the end result is this thing I've called Baochip. It's a marketing under the name Baochip, the Bao1X. It's a partially open SoC for high assurance applications. It's got 4 megabytes of on-chip ROM, 2 megabytes of SRAM, some cryptographic accelerators, a bunch of peripherals and I/O, these sorts of stuff, and a few open source CPUs. The source code's out there on the internet. I haven't made a big noise about it, but you can just go to this repo here and you can get the whole source code for large portions of the SoC. There's still portions of closed source, like the bus fabric, and of course the Cortex M7 is not open. But you can still get my CPU, the peripherals, and cryptography and start looking at them, playing with them. Right. So why is the source code really interesting from a high assurance perspective? Well, it allows you for better integration at the system level. So instead of using GDB for a debugger, you can use Verilator. Have people heard of Verilator? Anyone here coded in Verilog? People done this sort of stuff? Okay, I'll go over it briefly a little bit. But basically, if you have the RTL for a chip, you're no longer having to deal with GDB to debug a chip. You basically have God mode view into the chip. You can look at every single bit of state inside of a chip to uncover your bugs at the end of the day. You can have direct proof that your constant time code is constant time. You can see it in the waveforms, how much time your code is doing. You can see the pipeline bubbles visually. You have zero overhead performance profiling. You want to go between kernel and user space. You don't have to instrument it with something. You run the simulation and you have the trace and you can go ahead and pick these things out. So this is what God mode view looks like into SoC, right? So this is the CPU. I've just picked out a few vectors. At the very top, there's a program counter that's coming along. I've rendered the program counter visually, so you can see it's kind of going up, because that's what program counters do typically. They increment upwards. And then I can say, okay, well, these are the registers that are being fetched. This is the register file output. This is the ALU logic that's going. You can notice you can go forward and backward in time. For any given code piece, I can say, here's the bug. I can now go backwards because it's in the trace of the simulation at the end of the day. It's no more like, I have to print F or find something or trigger GDB. You just sort of capture the trace and look for it at the end of the day. And I wrote a little extension to a thing called to GTK Wave, which allows me to now hover over the program counter and correlate that with the line of assembly code that the CPU is running at that point in time. So you can basically take that trace. You can say, okay, what am I doing? You can pull up the assembly code and say, this is what's executing inside the CPU. You can say, why is there a pipeline bubble? Why is there a stall? What's going on? And then you can basically just debug your code like this. So I don't need GDB at the end of the day. I have Verilator because I have the RTL for my SoC. And you have it too now because this is now an open source SoC. Anyone here can go ahead and debug their codes and get good confidence using this type of tool. So I think this is actually one of the bigger, people say, RTL, without the PDK, what use is it? How do I know what's going on inside the chip? Well, at the software level, you have a lot more assurance as to what's going into the chip with RTL. In addition to sort of doing the chip itself, I decided to have a little fun on the side. So I'll take the last few minutes to talk and tell you about a little thing I put in there just as for the lulz, a little bonus project. I built a little I/O emulator in it. I call it the BIO. It consists of 4 Pico RV cores that are tied together with a network of FIFOs. And it basically, you can emulate any line protocol with a 25 megahertz toggle rate or less. So CAN, LED strips, 10 megabit Ethernet, used to be full speed smart card interfaces. infrared protocols for wacky, like, air conditioners, whatever it is, you don't have to say you're sorry. You can basically software-defined peripherals, right? So you can compare it to like the PIO and the Raspberry Pi, except this one's open source and doesn't have patents on it. And so very briefly, how to BIO. This is a view of two of the cores. And what I did is I took a Pico RV, and people may know that RISC-V normally has 32 registers. If you do an RV32E, you get 16 registers. But the opcode space still encodes for 32. What it is, they took the top remaining 16 registers and direct map them to the peripherals. Right, so if you move to a particular register, you go ahead and set an I/O. You can read from an I/O, or you can talk to a FIFO. So if you want to go ahead and toggle a GPIO, it's as simple as doing move, x21, x1, right? And so you say, well, to talk to a GPIO on a regular thing, you do a load store. The difference, load store semantics don't have fixed time. You basically have to deal with the amount of cycle delay that's going through the AXI bus or whatever it is. You don't get cycle accurate I/O. By putting it architecturally into the ISA, you have guaranteed cycle time accuracy on a GPIO bit bank, right? Now, if I want to talk to one of these other 4 cores, the way you would do it is you basically go ahead and put a piece of data into a FIFO. It's as easy as just moving thing into a register. So go ahead and move X1 to 16X1, puts the data into the top of the FIFO. When the FIFO gets full, the CPU blocks and stops putting data in. So it has a natural sort of synchronization mechanism built into it. If you want to receive a message, you want to get or wait from a FIFO, you can basically read from a FIFO. If it's empty, the CPU will block. So now you can imagine if you had one core and you want to have lockstep synchronization with clock with 3 other cores, the first instruction the 3 other cores does is read from an empty FIFO. They block. Then one CPU core says, okay, I'm just going to throw a number into the FIFO that starts everyone off on the next cycle together, and now you have clock sync across 4 cores instantaneously, and you can go ahead and start banging the GPIOs independently for the pins you care about, right? So that's basically the interaction between these different cores. Finally, there's a mechanism for synchronizing to external events. The same thing that we use to block on empty FIFOs, we can use to block on a clock edge. So if you want to run a low slower clock or an external clock like SPI, you want to on a rising edge start processing the data, you can go ahead and trigger your CPU core off of an external event as well using the same mechanism. So there's a fun little thing they put in there. It's open source. Might as well have some fun. Put something in there that's going to be something that has some utility and maybe also can have a little fun programming. 4 Pico RV cores running at 700 megahertz clock gives you about 150 MIPS. Deterministic cycle accurate I/O. You have a 4K private memory associated with them. And it's about never having to say you're sorry about I/O, right? So there's a lot of it. When you go to SoC guys, there's a lot of hand-wringing. Oh, do we have 4 UARTs or 5 UARTs? Do we have 2 SPI blocks or 1 SPI block, right? You have only so many I/O. It's software defined now. So we can basically have whatever you want within the realms of the 32 pins they can control. And you can actually do things like error checking and hardening of protocols inside the hardware accelerator now. So if you're doing like a little TCP accelerator, you can go ahead and check the packets before they even get to the CPU, unpack them and deframe them and so forth. Putting it all together, so this thing is a mostly open RTL SoC built for inspection. So on the left-hand side is a picture of the chip itself. You can put it on a board. I actually have a few of these boards here, so if you're interested in playing around with it, come talk to me, find me. I'm happy to give a few of these boards away to people who will actually do something with it, and not just put it in their desk and have it sit there doing nothing. Very early silicon. So these are like pre-silicon boards. And then you can, of course, view it with iris, right? So this is, that's an iris view of the chip. Again, I showed you earlier the floor plan of the chip, and that's the iris view of the chip. You can see visually that this is probably the right chip. You have some assurance that this chip is the chip they say you're going to get, which is unusual for any chip targeted towards security applications. You only have the NDA to even see what blocks are inside the chip. So I'm just going to go up in here on stage and say this is what the chip should look like. And then hopefully you can get the chip and say, ah, yes, I have the chip that Bunnie's talked about, and I know that's going to be the chip that I'm going to use. Higher assurance doesn't end at silicon, so there's this whole story I just told you about the silicon stuff. I don't have time to go into all the stuff that goes into this, but many secure chips get hacked by software vulnerabilities. The Baochip-1x has an MMU on the inside, so it has hardware memory isolation. It's a 60-year-old idea, but somehow our IoT devices do not have MMUs in them, and we don't use virtual memory. It's mind-blowing. I don't understand it, but guess what? We have a RISC-V core we can put an MMU, we're putting on the chip, right? And then I wrote an OS, Pure Rust OS called Zeus. It has virtual memory, a microkernel, Has a standard library. You can go ahead and so you have a pure Rust layer basically running on top of it. So you have higher assurance also at the OS level on the chip as well. So it doesn't just end at the silicon. You actually have a whole story going up the chain. That project is all open source. You can just check it out online, fork it, play with it. So, wrapping up, this is a kind of a roadmap that I'm laying out towards higher assurance silicon. We're not there yet. It's a lot of work to get to the goal of truly high assurance silicon. But it's very simple. Roughly, there's two elements. Make it inspectable, and then inspect it, right? So make it inspectable is open silicon. Let's talk about open designs. Let's talk about getting the actual PDKs open at the end of the day. And the example I gave today is the Baochip-1x. It's partially open chip. It's not fully open, but it's open at the RTL level. But it eliminates a lot of guesswork for people who wanted to red team it. I've done a lot of the hard work for you. Don't have reverse engineering. Just look at the RTL, look for the bugs. Go ahead and find them, please. This whole idea is that we're going to try and improve this and make it better over generations. I invite people to go ahead and find these things and make it better. Engage with the ecosystem, build documentation, build better drivers, right? And then inspect it, right? So point of use inspection, Iris, a technique that I've been looking at, allows us to look at these chips, have some assurance that this chip is the chip that I said I'm shipping to you, not some chip that some malicious adversary substituted in the supply chain. And you can do it at the point of use without destroying the chip itself. So the actual chip you're going to use is the chip you inspect. A lot more work to come. Fully open PDKs are a long way off. Electrical scan chains and so forth, as I talk about, that's a bit out there. Finding and fixing all the bugs takes a lot of work. So this is not going to be perfect on the first round, but open source isn't born perfect. It's born of participation. So I'm asking people here to try and help me with this, participate in the project, find bugs, help me make it better, help and make it better for the community, and hopefully we can get towards a higher assurance silicon at the end of the day by all working together. And that's the talk. Thank you.
Thank you so much. Thanks, Bunnie, for the keynote. And we have a couple minutes for questions. Do we have questions in the audience? Don't be shy. Oh, yeah.
Hey, very great talk. Thank you. So I guess you look mostly into microcontrollers. Have you also considered just general purpose CPUs, talking about the OpenC910 or OpenC96 from Tiet, for example?
Oh, you mean like the stuff you'd put in a laptop or?
Yes.
Yeah. I mean, that is also interesting as well. That's a whole different class of complexity and tape out. The reason why this one came up first is, as I mentioned before, I'm hitchhiking on a SoC. Most of that chip was not designed by me. I just stuck an open source core in it that does things. And so this is the first step. I think in the long term, absolutely, we'd love to see fully open source, general purpose processors.
What I'm mainly interested in here is if you could basically check, they released the open source code for their silicon. So we have silicon and open source code. Mm-hmm. If you would be able to basically diff these two designs, if they are the same, if the hardware that they ship is actually the one that is open source.
Yeah, I think at the end of the day, depending upon, if you had a fully open PDK, you could get the GDS2, the mask sets, you can basically do the diff. When we design chips, we have this thing called LVS, layout versus schematic, that we do, which is essentially a hardware diff up to the RTL. And they have formal provers that can, go ahead and say that this gate level netlist matches the RTL. So we can go all the way back if we had a fully open supply chain. But even without that, we can put bounds on it. We can say okay, there's so many gates in here. There's so many gates that should be created by this RTL. If there's a lot more gates in there than there should be, then we know something's going on. So it's a sliding spectrum what we can prove and say. But the more open we get, the more we can prove, the more we can constrain, the more confidence we can get. Yeah. Yep.
All right. So we have another question on the other side.
Hi. So if we were to look at using the Iris technique in the near term, right, because some of us have things we want to look up now, not in 15 years. I'm also assuming that manufacturing designers aren't really open to sharing any of this or changing their copyright laws in the near future, right? That's probably going to always be an issue. They want to make money. Some people want to actually help, sure. But yeah, how do we get around sharing what we know is correct silicon or correct layouts that, right, they're not willing to say this is ours? Right. And how do you know you're not just looking at bad engineering, them covering up their mistakes that they've found?
Well, at the end of the day, we can never, is it a bug or is it a backdoor is a classic, one of those, like, I forget what those diagrams are of, like, the candlestick and two faces kind of thing. Like, is it a bug or a backdoor? Same image, same different interpretation. That's a philosophical question. I can't necessarily answer that. But in terms of imaging a chip, you can always take a picture of a chip. There's unless you signed an NDA that says you promise you'll never take pictures of the chips or something like this, did something like stupid to yourself, like you can take pictures of the chip and put them out there. Now, will the manufacturer say, for sure, this is my chip? Will they vouch for it and authenticate that? They may or may not, depending on who they are. But if you get, and part of their reason for getting this iris out there and making it cheap is to have everyone taking pictures of chips. At some point in time, we agree upon this is what chips are looking like for all of us. And if one of them looks different for any of us, then we know that that one's an interesting one to look at the end of the day. And so the theory is not as much about, with iris is essentially, if you can get a manufacturer to put the reference images out, great. A+, right? But barring that, at least having sort of herd immunity against the backdoors is kind of what we're looking for at the end of the day. And to a first order, because there aren't any iris images out there of anything. If you showed me a die shot, I'd be like, I have no idea, is this backdoored or not? But if I had a database of things to go to and everyone here had taken a picture of their chip and said, this is what it looks like, and say, well, at least 200 other people have the same chip as me. So either we're all backdoored or none of us are backdoored. That's a bit of information that we have that we didn't have before. So that's about as good as I think we can get.
Is anyone willing to make that database at this point in time?
Yeah, I mean, the Silicon Prawn chip server that I put things up to, they collect die shots. So there's a whole community of people who are like, internet has everything, right? And so guess what? There's a good community of people who like taking pictures of chips on the internet, and they upload them to a server. So that exists. Yeah.
All right. Last question for now from here.
Thank you. What's the state of tools for silicon design in open source? Is it still the big commercial vendors, or the open source tools are mature enough for the full flow synthesis and everything?
Yeah. The synthesis stuff is actually, there's a tool called Yosys out there that's actually does a pretty good job of synthesizing. I think probably the biggest weakness is around the place and route, because we don't have access to the PDKs and the detailed stuff. We can only target like these academic approximate libraries and whatnot. And then probably the weakest link is going to be verification, because we don't have actual Foundry rules to start saying, are we meeting timing? Are we doing the corner extraction and whatnot? So there's some gaps to be filled there. But these guys like the Tiny Tape Out, what they're doing is they're by practicing these pipelines, getting people to make chips, finding the holes, they're kind of filling these methodology holes in at the end of the day. And also the nice thing is open source, they're doing, the formal guys inside industry will be like, wow, they're a bunch of yahoos doing crazy stuff, but also they're just being innovative. I think there's a lot of really interesting techniques that haven't been explored by the EDA community that they're looking into. So I'm also kind of excited to see what comes out of that sort of stuff. And then obviously this whole wave of AI and ML, whatever sort of stuff. But you can imagine it actually might be pretty good for chip design, a lot of pattern recognition and placing of things and whatnot. And, the open source community is a little more facile, more agile ability to sort of adopt some of these newer techniques. So it's a possibility even they could eclipse it over the years.
All right. Thank you, Andrew. If you have more questions, then you are staying here for 2 days.
Yeah,
right?
I'll be around. And like I said, I have some of these boards on me. Come find me. I don't actually literally have them at this very moment. They're upstairs in the hotel room, so don't come to me right now and demand one. But you find me later on the conference. And if you want to find out more about the chip and whatnot, the Blue Sky handle's up here. You can follow that on Blue Sky, and I'll be posting updates there. So,
thank you so much. Yeah. Let's give a warm round of applause to Bunnie.